Hello and welcome back for part 2 of our workbook review. So now we will be taking a look at the few circuit problems that I have assigned you from the workbook. That's 16.4.7, 8, 9, 10, and I believe 12. Again, all the problems are going to be up here as well, so if you have not done them yet, please feel free to pause the video, try them yourself, and then look at the solution. Alright, without further ado, so complete all the last three cells of each table that follows. For the circuit shown in the first cell, do not solve for the currents. Okay, so we're not actually solving, we are just plugging in, we're just filling in the table, and then in this one, we actually have to determine the current and the potential difference across each resistor. Alright, so the junction rule. If you recall, the junction rule says that the sum of the currents in has to equal the sum of the currents out. Alright, that means that what I'm going to do is I'm going to give a name to each current running in this circuit. Okay, so we're going to call this I1. I'm going to call the one that goes to this branch I2, and then the combination here of the currents going through this one is going to be I3. And so what you've got is you've got two batteries here. You've got each of these giving a current going this way. This one's going this way, this one's going this way, and then they both join up at junction A and come up through here. So in junction A, we've got I1 plus I2 is equal to I3, and then here, coming out of junction A, we've coming out of junction B rather, we have I3 splitting up into I1 and I2. So I3 is going to equal to I1 plus I2. Simple as that. And apply the loop rule for 3 different loops. Okay, this is obviously not enough space, so I'm going to cut it out here and do it here. So the first loop I'm going to do is the big one with the 9-volt battery. So starting with the 9-volt battery at this point, I guess, we're going to go from 0 to 9. So we've got 9 volts. Following the loop around in the direction of the current, we then come to this resistor. So we got minus 7 ohms times I3. And then coming back up around, we've got minus 1 ohm times, I guess this is I1. And this all equals 0. And that's this loop up here. Alright, so yeah, let me draw that in. Alright, switch colors. Now let's do this loop. Call this the red loop. So starting with the 4.5 volt battery, we've got 4.5 volts minus, again, 7 ohms I3. And then going here, we now cut through this one. We've got minus 0.5 ohms times I2 is equal to 0. And now it wants a third loop. The third loop that we're going to use is actually going to be the loop of the two of these, the two top ones. I guess I was supposed to have drawn these arrows here, but that's okay. So this last loop, I'm going to go like this. Alright, so we've got, I'm going to start with the 9-volt battery again. So we got 9 volts minus, now it's going through the second battery but backwards. It's not going in the direction of current, it's going backward to the direction of current. So this is going to be minus 4.5 volts minus so now because this is going the other direction against the current, it's not going to be minus 0.5, it's actually going to be plus 0.5 ohms times I2. And then going up here, it's going to be, now we're back in the direction of current again, so it's minus 1 ohm times I1. This is all equal to 0. Alright, there you have your 3 loops, there you have your 2 junction rules, and so now what we can do is we can move on to the next portion, which asks us if this is all true, then for the circuit in activity 16.4.7, determine the current and the potential difference across each resistor. So essentially what we need to do is we need to find the current first, and then we can apply those currents to the different resistors and find the potential difference. So what we have here now is we have 3 equations, technically 4 if you can consider the junction rule, and 3 unknowns, I1, I2, and I3. So all we have to do is find a way to combine these equations to then give us what we need. So what I'm going to do is I'm going to actually ignore this. Actually, I'm not going to ignore this. Yes, I will ignore this. I'm going to ignore this one. I'm just going to use these top two, and I'm going to use the junction rule. Because what I can do then is I can take each of these equations, define I3 in terms of I1 and I2, and then solve for I1 or I2 in each part. Like this. So first I'm going to take the junction rule and I'm going to plug this in for I3. So I've got I3 in terms of I1 and I2 for both of them. So for the first one, I've got 9 volts minus 7 ohms times I1 plus I2 minus 1 ohm times I1 is equal to 0. And then I've also got 4.5 volts minus 7 ohms times I1 plus I2 minus 0.5 ohms times I2. Well, 0. I'm going to simplify and distribute, or rather I'm going to distribute the 7 ohms to both of these, and then I'm going to combine like terms, which is going to give us something that looks like this. Video magic. Alright, and now we have two equations. So again, what I've done is I distributed this -7 to each of these i's in both equations, and then I combined like terms. So in this one, you've got -7 ohms minus -7 ohms times I1 minus 7 times I2 minus 1 times I1, so I've combined the -7 and the -1 to give me -8 I1 minus 7 I2. Then I did the same thing for this one. Now what we have to do is we somehow have to cancel out one of these i's, either by solving for one and plugging it in, or by doing a sort of where you multiply one of them by some number so that when you add them together you get one of these to cancel out. Unfortunately, that is going to result in a really weird number, especially because of the 7.5 here. But unfortunately, that's what has to be done. So what I'm going to do, I'm going to try and cancel out the I1 because it'll be easier. So if we try and cancel out the I1, we need to find a way that 8 I1 cancels out with 7 I1. And the only way that I can see, unfortunately, is multiplying one of these. I'm going to multiply this by -7, and I'm going to multiply this by +8. That way we end up with 56 for both of these, and that'll cancel out. One will be negative, one will be positive, obviously. So here goes nothing. Let's do a little bit more video magic again. Alright, that was exciting. So again, I took -7, multiplied it by all of these, and then I took 8 and multiplied it by all of these, which gives us these lovely numbers. But now what we can do is we can take both of these equations, we can add them together. That's why I multiply by negative, so I can add and not subtract. It makes things easier. So we get 63 minus 36, which is going to give us -27. This cancels out. And 49 plus -60 is -11 I2 is equal to 0. Alright, and now solving for I2, we get I2 is equal to 27 over 11, negative. Now, you might be thinking to yourself, first of all, this is a gross number, which it is. I apologize for that. If you want a less gross number, I would plug in the decimal, which is going to be 2.45 repeating. But we can just call that 2.45 amps. And you'll notice it's negative, okay? What does that mean? That means that our assumption that the current going through the battery, going through this wire, was going this way, right? So we said, we thought that the current would be going this way, and then this way, right? What's actually happening is not that. Because we got I2 to be negative, it means that the current is actually going the other way. So in a test problem, if you were to see that, I would make sure to go back and fix that. And I didn't believe it either, but So what I did was I went and opened up the circuit construction kit, our good friend, and I'll pull it up here, and you'll notice, now remember, the blue dots are the electrons, not the protons, not the positive current, so to speak, which means that the positive current is moving in the opposite direction that the electrons are moving. And you'll notice that that means that this current is going this way, and that in this middle one here, it is actually going the other direction. You'll also notice in this case, for example, that the electrons are actually going up through this battery in the wrong direction, which happens if you have two batteries that are not supposed to be together. So yeah, so our current is actually running the opposite direction that we thought in this middle wire. Crazy, I know. So that is it. So I2 we know is 2.45 amps, going to the right, not to the left in this picture here. And then it's just a matter of plugging this 2.45 into any number of these equations here to find out what I1 is. Let's put it into this first one, the 9 volts minus 8 I1 minus 7 I2, which will then, if we plug that in, will look like 9 volts minus 8 I1 minus 7 ohms, right, times 2.45, which when we solve for that will give us roughly 1.28 amps is I1. So also don't forget, I realized I forgot here, this needs to be negative, which means that this whole thing together is going to be positive. When you're going through this, that'll give us a positive current for I1. All right, now that we have our I1 and I2, it's just a matter of plugging these into our currents here and solving for I3 to then find out what the potential differences are on each resistor. So for example, just to do one, if we want to find the potential difference across I1, across the 1 ohm resistor, it would just be 1 times I1, which is 1.28, so the potential difference across this would obviously be 1.28, and so on and so forth. All right, again, so potential difference across each of these is just taking the current that's going through each one and then multiplying it by the resistance. All right, let's move on. Evaluate the solution. I like these. So apply Kirchhoff's loop rule for 3 loops and the junction rule for 1 junction of the circuit shown at the right, and do not solve for the electric current. So proposed solution, we've got 9 volts minus 7I minus 6I, 9 volts minus 7I minus 3I, and then 6 ohms, negative 6 ohms plus 3I time plus blah, negative 6 ohms I plus 3 ohms I equals 0. So while this looks great and all, I will say one thing. This person neglected to do a junction rule. So there's no junction rule here. This is 3 loops. Let's make sure he did them correctly. So he started off with a 9-volt battery for all of them, and then went to the 7 ohm resistor first. So it looks like he's actually going backwards. So this 7 ohms I minus 6 ohms I. So this one is actually this loop here. This one looks like it's going to be this outer loop here going this way, right? Because it goes to the 7 ohms after going through the battery. And then this last loop, which I'll make in blue, looks like it's going this time. The direction that it's going in is negative 6 ohm I, which I guess means he's going this way. Well, it depends on if we assume, I guess, if this person knows what they're doing, because they've messed up these two, and I'll explain why in a sec. But because they messed up these two, I'm going to assume that this one is not correct, which means he thinks it's actually going this way, this loop. What's wrong with these first two? So these first two, because the 7 ohm ones come second, I'm assuming they're going straight from the battery to the resistor, which means that they're actually going in opposite the direction of the current. The current is going in this direction from the big side of the battery, going out like that. The loop they're taking is going the opposite way, which is fine. It just means that this has to be, to correct this has to be negative, this has to be positive, this has to be positive, Same here, negative, positive, positive. And then if we're assuming consistency of him being wrong, then this would be positive and this would be negative. Or we can assume that he took the same loop going each way and then assume that this one isn't wrong, in which case maybe let's do that instead. Just give them some benefit of the doubt. So let's say then this is actually going the correct way of going the same way that he went with the other two loops, so this way instead of the other way. All right. So these two are wrong in that the signs are wrong for the way that he went about going through the loops. Otherwise, everything is right. So this would be the corrected solution. And then again, oh, and there's a junction rule missing. Also, this person needs to have defined an I for each current here, right? So if we've got, say, I1, I2, and I3, then this would be I1, and this would be I2, and then this would be I1, and this would be I3, and then this would be I2 and I3. You have to define the actual values for this current, because if you don't, then you're going to have a bunch of the same I, and the solution is going to be all weird and wrong. All right, moving on down. Okay. So this is a circuit jeopardy. So based on the values that are given across each element, you are supposed to define what the circuit looks like and draw a picture of the circuit. Of course, it doesn't really matter. There's multiple ways that you could draw this circuit, but what I'm going to show you is just one possible solution. So here's what we have. We have a maximum potential difference of 8.86. I can only assume then that this element must be the battery. So let us take a battery and call this, it was a bad battery. Call this 8.86 volts. All right, that's a weird potential, but it is what it is. Then we have these three elements, whatever they are, besides the battery, so I guess these two elements that are showing a current of 0.071 amps. So that stands to reason then that each of these must be in series with the battery so that their currents all stay the same. So some element here, which we will call element 2, some element here, which we'll call element 3. Now you'll notice if we then look at these two, right? These two both have the same current, so we want to assume that they're also in series, but you'll notice that they also have the same potential difference. Now, these things cannot be in series with this, right? But they also can't be, these two things can't be in parallel to all of this, because then there would be a third current, right? If you picture a circuit that looks something like this, then we'd have our battery and all those three elements, but then these two parts of the circuit would have different currents unless they were equivalent, unless they were the same current, right? So our loop rule, if we did a loop rule that looked like this, or I guess the other way, but whatever, and like this, if we did these two loop rules, then we would see that the two currents here and here would have to add up to this one. So you'll notice 0.035 plus 0.035 is going to be 0.07, roughly 0.071. So I think it's safe to assume that these, if we do have a circuit drawn like this, then these two parts of the circuit have to be identical. You'll also notice that in the loop rule, not the junction rule, okay, the loop rule, we would have to have, if we have this element here, that is this one, right? We've got the battery, which is 8.86. The potential difference across this, and whatever is inside these two loops would have to add up to 8.86. So you'll notice we've got 7.1 plus 1.76, which is 8.86. So if this is how we want to draw it, then these two circuits, these two parts of the parallel have to be the same, which means that these two elements are actually not in series, they're actually parallel to each other. And these three elements are in series. All right? So what we can do, we can draw it this way, or we can do another way we can draw this is we can say just that whatever these two elements are, There's a split here, and then these two elements are parallel. Now, let's look at this third element. So this third element, we're saying it has a potential difference of 0 volts. Really, all that means is that there's actually no element here, and it's just a wire. So, you know, we can have a ammeter somewhere like in there for ammeter 3, and then the potential difference here is just going to be 0 volts. If we have a potential difference of 7.1 here, that means that our resistance, you know, delta V is equal to IR, or I is equal to delta V over R, so R is just going to be equal to delta V over I, which for this 7.1, if we take 7.1 and divide it by 0.071, that is going to give us roughly what? 1, 2, 1, 2, 3, 5,000 ohms, I think. About 100 ohms. So this is, we can make this a very weird looking 100 ohm resistor. And now let's take a look at these two resistors. So because there is a potential difference across them, there has to be an element here. We can make these both resistors. They would be equal, they'd be identical. And using the same equation, we get a resistance of about 50 ohms. All right, and there you have it. That would be a circuit that would fit this. And of course, the potential difference for each element would have to be fitted around the element, and then the current would have to be in series with it. So you could have an ammeter, say, here for the battery, the ammeter here for the resistor, and ammeters in each of these branches. Ammeter, an ammeter there for the two parallels. And then the potential difference across each one of these, you know, delta V, etc. All right. All right, moving on. Last one. So what is the potential difference between points A and B from here to here? If the EMFs of the batteries are 4 volts and 1 volt, and the resistance of the resistor are R1 is 10 ohms and R2 is 5 ohms. So again, this is 4 volts, this is 1 volt, R1 is 10 ohms, R1 is 10 ohms, and R2 is 5 ohms. So what I'm going to do is I'm going to do a loop rule for this circuit, and then just use the combination of two of these to then find the potential difference between these 2 points. That should work. And this is point B, obviously. I guess I must have gotten cut off. So, doing a loop rule, starting with the 4 volt battery, because it's the bigger one, we've got 4 volts, minus, I'm going to go around this way, minus 1 volt, minus 5 ohms, times the current. The current's going to be the same in everything because it's a series circuit, minus the 10 ohms times the current is equal to 0. So combining everything here and separating out each side, we've got 3 volts is equal to 5 plus, well, negative 5 minus 10 is going to be negative 15. So we've got 15 ohms times I, which means that I is equal to, did I assign this to you guys already? This looks familiar. Is equal to 1/5 of an amp. So that's 0.2 ohms. Oh, sorry, whoa, 0.2 amps, my bad. And then measuring the potential difference across here. So what we can do is we can take either side here, add the two potential differences together, and we should get the potential difference across each one. So for example, if we take, let's say, these two elements, right, we've got 4 volts plus, or rather, sorry, minus our current, which is 0.2, times our resistance, which is 10, which will give us 0.2 times 10 is 2. 4 minus 2 is going to be 2 volts. All right, and if you want to prove that to yourself using the other one, then we would have, again, minus 1 minus 5 times 0.2, which is also going to give us 2 volts, negative, but still. All right, there you have it. So those are all the problems, I believe. Yep. Good luck, and I will see you tomorrow. Also, one more thing. Since you watch this all the way through, I can guarantee you that I will include a problem that looks a lot like this, and I can also say that I will include a problem that is a lot like the analyze the solution, or determine as much as you can about a scenario type thing. Yeah, so thanks for watching. I hope you saw this to get this helpful tip. Please, if you did see it, feel free to not spread it to the rest of the class. That's it. See you later. Bye.